see. Okay, so we're going to continue now where we were last time. We were talking about a Taylor series. So let's define a Taylor series. Suppose the function has a power series expansion. So we write out the function like this. And here we're using again our base point as x0. And so one thing to notice here is what happens if you insert or substitute x0 for x. What do you get? Well, then f of x0 is equal to a sub 0. And in particular, now we know what a sub 0 is, right? A sub 0 is f of x0. So in this expansion, we know what a0 is. Good. So now differentiate. And I'm differentiating a little bit differently. I'm keeping this constant around, I'm keeping this group together. Although you don't have to, I think it's a lot easier to see what's happening if you do keep these grouped. So if I group those together, right, the derivative is just going to be a1 plus, and then I just get the 2a2 x minus x0 to the 1 power, 3a3 x minus x0 to the 2 power, and so on for a4 x minus x3 to the x minus x0 cubed. Good. Okay, now what happens if I put x0 in for into f prime? Well, you see what happens, right? I just get a1. And so now I know what a1 is. So this is the original a1, right? I know that a0 is f of x0, and I know that a1 is f prime of x0. Good. Now I differentiate again, and I get I'm keeping these multiplied out, right, so that you can see what's happening. And so I get 2a2 plus 3 times 2, a3, x minus x0, so on and so on and so on. Right, and so what happens when you plug in x sub 0? Now we know that a sub 2 is going to be f double prime at x0 divided by 2. Right, and so now I've got a2 nailed down. Good, and so what you can kind of see what's happening now, right? If you differentiate again, what's going to happen? The 3 times 2 a3 is going to pop out in front. Right, and so f double prime at x, or f triple prime at x0 is going to be 3 factorial times a sub 3, and then you see these other factorials are lining up behind it, right? And so now we know that the general formula for a sub n is going to be what? The nth derivative of f at x0 divided by n factorial. Very good. And so now we know what a Taylor series is. This is the Taylor series. So notice that we've always say that the 0th derivative, right, at x is going to be just f of x. So that's what it means to have n equals 0. Furthermore, does everybody remember how to define 0 factorial? 0 factorial is defined to be 1. Actually, there is a way to define it so that you don't just say this is true by definition, but that's the gamma function that we saw actually in the Laplace transform section. We didn't really go through that, but that's how you would prove it. Okay, so now we remember that we assumed that f of x has a power series representation. Well, does every function have a power series representation? In fact, let me go back there. This is what we assumed, right? We assumed that I could write f of x this way. The trouble is that not every function can be written this way. And if you remember from Calc 2, only certain functions can be written this way. We call them analytic functions. Right? So only analytic functions can be written as or by definition, a function is analytic if it can be represented by its power series expansion or Taylor series. Good. So let's move ahead again. So now we know how to find a Taylor series, right? And so the Taylor series for f of x is now defined to be f of x equals n equals 0 to infinity, the nth derivative at x0 over n factorial. By the way, this is, I should have tacked on a thing here, right? So the Taylor series for f of x at x0, x equals x sub 0. Let me say that one more time. The Taylor series for f of x at x sub 0 is defined as this. Okay, So this is the nth derivative at x sub 0 over n factorial times x minus x0 to the nth power. Very good. And of course we remember our Maclaurin series, yes? Oh, I can't do a Scottish accent. Oh well. The Maclaurin series is the Taylor series, but it's based at 0. Good. And so we know how to compute a Maclaurin series, right? And in fact, in Calc 2, we memorized a few Maclaurin series. And so those are the ones that we want to kind of remember as the template series. But just as a reminder, to find a Taylor series, right, and that's a question in some of the homework problems, you need an expression for the nth derivative at x0. So what you normally do is you start off with your f of x and you start differentiating it until you see a pattern. And hopefully we see a pattern. Okay, so the template Maclaurin series, some of the ones to start off with, if I just have 1 over 1 minus x, that is the sum of x to the n. And actually, does this look familiar? What if x was equal to r? Does that look familiar now? Yes, that is the geometric series. So we know that 1 over 1 minus x has this power series, but of course that's not true for all x, because for some x that's going to diverge. So this is the geometric series. Well, it comes from the geometric series. And whoops, what did I forget? I forgot to say when this converges. This converges for the absolute value of x less than 1. All right, but you knew that. Okay, so the next one, e to the x. So just to remind yourself what's going on here, this is the nth derivative at 0. So if I put in e to the x, all the derivatives are e to the x. So if I substitute 0 in for x, this is all e to the 0, which is 1. And so that gives us the power series expansion, or Taylor series expansion, for e to the x. Very good. All right, and then the other two you want to kind of, oh yeah, I put that in there. The other two you want to kind of keep together. By the way, can you find where this series represents e to the x? For what's the radius of convergence? You should be able to show that the radius of convergence for the exponential function is actually infinity. And that's the same thing for the sine and cosine down here. I just put these two together because you should remember these as a pair. So remember that the sine function is odd, and so the sine function is going to use the odd powers of x. And so this looks like a geometric, or not a geometric, a Taylor series, except for we're only using the odd powers, right? And then furthermore, the other weird thing about it is that it's an alternating series. So this is an alternating series that only uses the odd powers of x. Cosine, even. So this is still alternating, but it's only using the even powers of the expansion, right? Okay, so that's one way to remember how sine and cosine are related, right? Sine is odd, cosine is even, so sine is only using odd powers, cosine uses the even powers, and they both alternate in sine, plus, minus, plus, minus, plus, minus. Good, very good. So these are the 4 Maclaurin series that you should remember. We can find where the radius of convergence is for all 4 using the radius or the ratio test. That's not too hard. You might try it out. Good. So here's an example. Find the Taylor series for f of x equals x cubed minus 3x squared plus x plus 1 at x equals 1. Okay, so I have to give you the base point, by the way, right? So that means that your function or your series is going to look like this, right? It's going to be n powers of x to the x minus 1. Good. I don't know why I started that at 1. This should be a 0. Sorry about that typo. This is starting at n equals 0 down here. Good. All right. So let's compute the a sub n by computing the derivatives. The 0th derivative is minus 1. So a sub 0 is minus 1. The first derivative is 3x squared minus 6x. So so that means f prime of 1 is going to be minus 3. Just plug it in. And so that means a1 is equal to minus 3. Good. Second derivative, 6x minus 6. Second derivative at 1 then is 0. Good. So therefore a sub 2 is 0. And I just reminded you that, when you're computing your a's, those are the actual values of your coefficients here for the power series of the Taylor series. You need to remember to divide by n factorial, right? And so we're going to do that for the third derivative. The third derivative is 6, so we don't have to really evaluate at 1 because it's a constant anyway. But now a sub 3 is going to be the third derivative divided by 3 factorial, and so that's going to be 6 over 6, which is 1. Good. And now I've got all my derivatives and all my a's. Notice that every other a is going to be equal to 0, right? And so therefore, what's the Taylor series going to be? I just repeated myself up here so we won't have to keep flipping our slides back and forth. Good. So let's go ahead and compute the Taylor series. There it is. Oop, one more term. There we go. Good. I think that's it. Okay, so by the way, why was this a terminating polynomial? Or why did the series terminate? And that was because f of x itself was a polynomial of degree 3. So you would expect your Taylor polynomial to be degree 3 only, right? Good. And so this has a finite sum. And so just for fun, what's the radius of convergence? Did you say infinity? If so, you are correct. Why? Because you're only summing 3 numbers together. You can do that for any x, right? So the radius of convergence is infinity. And it's kind of a trick question, right? Because you're not, usually what we mean by convergence is it's a convergence in terms of a limit, but the limit is just going to remain constant. So we're not taking the limit, really, since you're only summing 3 things together. Okay, so the radius is infinity. If f is, okay, so we just said that, the polynomial of finite degree, so is the Taylor series. And so if you expand and simplify this expression over here, the Taylor series, what you should get is the original expression back. It's a bit of a pain, right, because you got to cube this out, but you can try it out if you'd like. Good. Let's try one more. Find the Taylor series of a function about x equals 1. I like x equals 1 here. And let's give it a try. I need to find a pattern in the derivatives. Y equals the natural log. Y prime is x to the minus 1 power. Okay, y double prime is minus x to the minus 2 power. Okay. Y3 is 2x to the minus 3 power. Let's do one more. We're looking for patterns. The fourth derivative is minus 3 times 2 times x to the minus 4. So let's see what kinds of patterns we see in here. This natural log is kind of a problem, right, because it's not like the rest of the patterns, so we're going to remove that from consideration. But we notice the first derivative has a minus 1 here, second derivative minus 2, third derivative minus 3, fourth derivative minus 4. So we know the nth derivative will have a minus n, right? Furthermore, let's see, the fourth derivative will have a 6 factorial, or I should say 3 factorial, which is 6. So again, the fourth derivative has a 3 factorial, third derivative has a 2 factorial, second derivative has a 1 factorial, and first derivative has a 0 factorial. Good. So far we know that the nth derivative will be n minus 1 factorial times x to the minus n, but then we have to take care of the plus and minus signs, right? So here we have a plus 1, minus 1, plus 1, minus 1, but we start with the first power being positive, second power being negative. So we can't just use minus 1 to the n, right? Because that would give us a negative here and a positive here. So we'll use like a minus 1 to the n plus 1 instead. Good. So now we know the pattern. There's the pattern for the derivatives. Good. And so that's for n greater than or equal to 1. And then of course we might notice that for n equals 0, right, we just get 0 for the natural log of 1 anyway. So we can just completely ignore that first term. Good. For the other terms though, we do want to remember that we're computing this at x equals 1 here, right? And so really then the our coefficients are just going to be minus 1 to the n plus 1 times n minus 1 factorial. Good. And then how do the factorials cancel? Yep, you're just going to be left with an n in the denominator, right? Very good. And so what have we just shown now? The Taylor expansion is minus 1 to the n. So this is the a sub n that we just found, but that only works for n greater than or equal to 1, right? Times x minus 1 to the n. Excellent. Just out of curiosity, what's the radius of convergence going to be? Here's a hint. What does the natural log look like? Does it have any vertical asymptotes close by x equals 1? There is one. There's a vertical asymptote at x equals 0, right? Because 0 is not and natural log of 0 is not defined. So what's the distance between the 0 and 1? That is 1. And so you should find that the radius of convergence is actually equal to 1. Good. And you can prove that by using the ratio test. Very good. Oh, I guess we're going to do one more example. Geez, I thought we were done. Let's try another one. In this case, you could compute all the derivatives, but let's see if we can use a template series to build a new series for the Maclaurin series for this function. And so for 1 over 3 plus x, that looks a lot like 1 over 1 minus x. And so somehow I would like to use 1 minus the series for this. And so what do I need to do first? I need to get rid of this 3. And so, yeah, I know that this is my series, right? So notice, by the way, if you replace the x here, like with generic object, then you have a sum of the generic object to the nth power. If that didn't make sense, don't worry, we'll look at it here in a second. So let's just look at the algebra here. Again, I want to try to get this 1 over 3 plus x to look like 1 over 1 minus something. 1 over 1 minus something. And so I'll pull out the 1/3 first, and so that leaves us with a 1 plus something. So how do I get the minus in the denominator? I just take the minus minus. So now I've got 1/3, which I'll just tack onto the front, right, of this thing. And then I've just got my 1 minus something in the denominator. And so now I can formulate my sum. Very good. I just pull out the 1/3, and then I've got minus x to the n over 3 to the n. And then, of course, you don't want to leave it in that form. Go ahead and simplify that. So that's minus 1 to the n times x to the n over 3 times 3 to the n, which is that. Wasn't that fun? These are kind of fun. Yeah, in this case, we didn't have to actually differentiate a bunch of times. We could use a template series to help us build the new series. Good. I think that is my last example. Yep. And so the next video is going to be on the algebra on the index of summation. See you then.